Consider a particle located at a point on a space curve represented by the blue curved line in a 2 or 3-dimensional space. The position of the particle is measured from a fixed reference point O, always a fixed reference point, and is designated by the position vector r equals r in general as a function of time. If during time delta t, the particle moves a distance delta s along the curve to a new position defined by r prime equals r plus delta r, then the displacement delta r represents the change in position. That would be the final position r prime minus initial position r, measured from the fixed reference point O. The average velocity of the particle during this time period is defined as v sub average equals delta r over delta t. One very important thing to notice here is that we have quantities in bold. So when taking notes on this section, anything in bold needs to be handwritten with a vector arrow symbol above it. Quantities in bold that represent vector quantities need to have the vector arrow symbol written. The instantaneous velocity at some moment in time is as follows. Vector v velocity equals dr by dt, the first time derivative of the position vector r. Since dr is tangent to the curve, the direction of the velocity v vector is also tangent to the curve. The magnitude of velocity, known as speed, is obtained by realizing that the length of the straight line segment delta r approaches the arc length delta s as delta t approaches 0. Thus, the instantaneous speed of the particle is v equals ds by dt. The average acceleration of the particle during this time period is a average. That average acceleration vector equals delta v over delta t, change in velocity over change in time. The instantaneous acceleration of the particle at an instant in time is vector a, the acceleration, instantaneous acceleration, equals dv by dt, which is also equal to d squared r by dt squared. Although velocity is always tangent to the path of motion, as we've discussed, it is important to recognize that acceleration is generally not tangent to the path, since the delta v vector is not necessarily tangent to the path. Often the motion of a particle is best described along a path that is expressed in terms of its x, y, z coordinates, i.e. using a rectangular or Cartesian component system. So looking at this image, we have an x, y, z coordinate system, this particle following this space curve in blue. And we have some origin here from which the position vector is measured or from which it is directed. And remind yourself of I, j, and k, which I usually say as I hat, j hat, and k hat. So we did cover this extensively in statics. I, j, and k are the unit vectors that have specified directions and a magnitude of exactly 1. The reason I say hat following ijk is that when handwriting these, they are vectors. Rather than using a regular vector arrow symbol, we use a hat symbol. It is the caret symbol, shift 6 on your keyboard, the upside down V symbol, which is used only and exclusively for unit vectors. Unit vectors, again, have a magnitude of exactly 1 with a specified direction. So I hat, let's recall, always corresponds to positive x direction, j hat, unit vector, always corresponds to positive y direction, and k hat always corresponds to the positive z direction. So if the particle at this moment is at point x, y, z, then its location is defined by the position vector r equals r as a function of time, where vector r equals x I hat plus y j hat plus z k hat. In general, vector r and the scalar coordinates x, y, and z are all functions of time. The magnitude of the position vector r, that is the straight line distance from the origin to the particle, is determined using the Pythagorean theorem in 3 dimensions, where the magnitude of position vector r equals square root of the sum of the squares of the components of that vector. The direction of vector r is specified by the unit vector. U sub r equals vector r over scalar r. Notice the details here. U is in bold. It is a vector, and imagine it with the vector arrow symbol above it. Subscript r to represent the unit vector for this vector r in particular. During an infinitesimal period of time, the displacement of the particle can be expressed as dr equals dx I hat plus dy j hat plus dz k hat. The instantaneous velocity of the particle is defined as follows. Vector v equals dr by dt. So in this context, that would be d by dt of all 3 of these terms. To evaluate each term, it is necessary to apply the product rule of calculus, taking a derivative, time derivative, of a product of 2 things. For instance, the first term, d by dt of x I hat, becomes the following. dx by dt times I hat plus x times d I hat by dt. Now notice this quantity here, d I hat by dt, is exactly 0, since the unit vector I hat does not change with time. It's constant in its magnitude and its direction. Evaluating the other terms in a similar way yields the following expression for instantaneous velocity, where v sub x equals dx by dt, v sub y equals dy by dt, and v sub z equals dz by dt. So in rectangular coordinate system using I hats, j hats, and k hats, the velocity vector v, which is dr by dt, equals the following in Cartesian vector notation: v sub x I hat plus v sub y j hat plus v sub z k hat. So the velocity vector v has a direction specified by the unit vector u sub v equals vector v over scalar v, and its magnitude, the scalar v, is determined as following: v equals the square root of the sum of the squares of the components. Each of the quantities, vx equals dx by dt, vy equals dy by dt, and vz equals dz by dt, can alternatively be written using the dot notation for time derivatives as developed by Isaac Newton. This is a convenient way to indicate time derivatives. So here's that dot notation. V sub x we can write as x dot, x with a single dot on top of it. Similarly, v sub y equals y dot, and v sub z equals z dot. This dot notation for time derivatives is used extensively in this class. It is distinctly different from the prime notation used for a general derivative with respect to any variable. So in calculus, we did use this prime notation. We're not using that in this class. It is distinctly different. Prime notation is very general. It can be any derivative with respect to any variable. The dot notation, on the other hand, is used exclusively for derivatives with respect to time. One dot above the variable, okay, like this x dot here with one dot above it, indicates the first time derivative of that quantity. Two dots indicates the second time derivative, etc. And as we mentioned, Isaac Newton developed this dot notation. The instantaneous acceleration of the particle is defined as follows, where a sub x equals dv sub x by dt, ay equals dv sub y by dt, and az equals dv sub z by dt. So acceleration a, that vector, as we know, is first time derivative of the velocity vector. That equals a sub x I hat plus a sub y j hat plus a sub z k hat. The acceleration vector a has a direction specified by the unit vector u sub a equals vector a over scalar a, and its magnitude, the scalar a, is equal to a equals square root of the sum of the squares of its components. That is, a equals square root ax squared plus ay squared plus az squared. The dot notation that we just mentioned can also be used for the components of acceleration, where a sub x equals vx dot, that equals x double dot, ay equals vy dot, that equals y double dot, and az equals vz dot, which equals z double dot. One dot is the first time derivative, two dots is the second time derivative, and these dots are always representing derivatives with respect to time in particular.